me share my let me share my screen and we go from there. Uh, I'm Sadra Hamadi. I'm going to be joining Siemens Mobility as the requirements manager, and this is a real honor for me to be able to talk with you guys about case studies uh, on the SC Handbook version 5. Uh, so there are 5 case studies outlined here in chapter 6, but there are references for other ones if you're interested in, if you're curious to see more implementation examples, there are references for those as well. So the reason we are doing this, the why of this presentation is, first of all, uh, it's important to note that INCOSE exams are more about processes, IPOs, methods, interrelationships of SE, and concepts. They're not going to ask you about people or stories, but there could be questions that they reference examples or these case studies. So what we're going to do in this session, which I think would be about an hour or so, we're trying to glue, things that you learned from the previous sessions with some, use cases or some case studies here. But the important thing is still the underlying principles, and it's not about memorization. It's just about understanding why, what were the challenges in these case studies, how the processes were tailored, right? Uh, and the techniques, input, output, tools and techniques. And one thing that I'd recommend is in your own time, first of all, please read the SC Handbook. This should not be a replacement for that. And also, if you have time and interest, I'd recommend practicing IPO identification, trying to find the correspondence between these case studies with the IPOs. And I'm gonna talk about an example shortly in the case study 1. So number 1 of the 5, this is about a medical device or medical device safety issue. The Therac 25. This is you can see a newspaper cut on the left, and on the right you can see uh, a body of water that is trying to mimic a patient that's going through that radiation therapy. This is just to give you some context about what it is. You can imagine these are high energy beams, and they're inherent hazard there, right? So Terac 25 was a dual mode, meaning that it could emit X-ray, high energy, or electrons. Medical linear accelerator, we call it LINAC, or they call it LINAC, developed by Atomic Energy Commission Limited, AECL of Canada, in 82. So this is an example of some tragic accidents that were because of improper practice of systems engineering. LINACs are used to treat cancer. So the energy of these beams is correlated with the depth of penetration of the beam into the tissue. So if the device should have been able to control what's the depth through which the beam is going to penetrate, and is it a cancerous uh, tumor, or it's just normal tissue. So it was an interesting technology, but it caused 5 deaths, and it's ranked in the top 10 worst software related incidents on many lists. So It's interesting to see why. Some background. You see, Therac 25 didn't came out of the blue sky. It had two precedents, the Therac 20 and 6. These numbers are the energy in terms of mega electron volts of those devices. You can see as in 76, lower energy, 82, more energy in 1 year, they increase like 20% or so, 25% increase in the energy of these devices. Interestingly, the previous versions or baselines of this medical device were safe, were really safe. And that was ended with the Therac 25. The big picture, the real reason is that they eliminated a redundancy mechanism for safety. For example, you can see that both the 20 and 25 had the controller software, but Therac 20 had hardware mechanisms, mechanical interlocks for safe operations, whereas in Therac 25, they said, oh, we don't need to spend that much money on the hardware. Software can do everything. That was one issue. And then lack of verification, enough verification to make sure that that's the case. So this is, kind of the most important point in this case study, lack of redundancy or improper safety analysis, risk analysis. And tying back to the previous chapters, we can say that this is a brownfield or legacy development. Why? Because it was built upon the Therac 20 software, right? And that was built upon the Therac 6 software. One odd thing in this case study is that only one programmer did the development and I assume testing. So they say the developer and tester should be two different, entities, people, whatever. But here, one person did everything, and that caused some amount in the catastrophic result. And another thing is in the Therac 25, they tried to, or they aimed at significant adjustments to be made for simplifying the operator interface and minimize data entry. So more automation. When you're trying to automate, it's very important that you do a full coverage test of what can go wrong, different sequence of inputs, race conditions, all of that. And one person, I mean, it would be difficult to cover all of that. At the end, because they classified it as a class 2 medical device, the reason for that was that they said, oh, the software is based on the previous certified models, and they used pre-market equivalency to, certify that, which was a contributing factor. And the errors that were introduced in this whole in this life cycle started from the concept and early development. So the decision to only modify the previous software and use it for this new higher energy version, right? It has more energy. The physics is different. The system architecture is different. You don't have the hardware. So that was a poor decision. And as well as, besides that, the documentation for the previous software was poorly, drafted. Only one person could understand, the developer could understand the logic. It's very hard to read somebody else's code, and you all know that. And the handbook says these are unfortunately still relevant. there were similar deaths for similar reason in 2007. So it means that, you know, the problems are kind of the same, but they change shape or form. But back to the Therac, they recalled it, and besides, you know, losing 5 people, precious life, and you know, loss to their reputation, the AECL had to pay over $150 million for compensation. So it would have been best to spend tenth of that in the early development for requirements or risk analysis before, you know, going through, you know, going to the rush, faster, better, cheaper, and you know, then the result is catastrophic, right? Uh, the handbook says these accidents are associated with the non-use or misuse of numerous SE practices, especially system verification validation, risk management, and assessment and control. And I really think you all can see why. Lots of software engineering good practices were not followed. Design reviews, you only have one programmer, lack of documentation, comprehensive software unit and integration tests. You know, they didn't do the full coverage test. They mentioned management inadequacies, overconfidence in the software, and also importantly, removal of the redundant hardware interlocks. Their practices were not okay or, you know, standard, and their risk assessment was unrealistic. In the CBOC, it's mentioned that in their fault-free analysis for the 25, they didn't even consider the chance or, you know, probability that the software can, you know, perform poorly. So when you don't plan for it, then you're not prepared. And unfortunately, that was what happened. But again, this was a case study, but what I suggest for everybody who's interested is to try to tie that back to the IPOs, right? So looking at this risk management process, what was the corresponding elements of this case study with this? I think we can say that, or I came to this conclusion that risks were not analyzed correctly. They lacked the risk analysis part. Risk management uh, was not planned. There's a good likelihood for that. Risk register was not correct and complete. They didn't consider that. So, and so on and so on. And you can add more to it. For stakeholder needs and requirements definition, their life cycle concepts was not, I mean, this is my conclusion, we can discuss, but I think it's safe to say that they didn't analyze their life cycle concepts correctly. The constraints on solution were not identified properly. The problem statement was not aligned with the real need of the stakeholders. Preparation most likely was insufficient. So these are just examples, but I suggest for all case studies, try to tie back to the IPOs. System architecture. So decision to remove the hardware interlocks means that the architecture was not conceptualized, evaluated, and elaborated. Conceptualized, evaluated, elaborated correctly. And I mean, they could have chosen other architectures. And I don't know what was the process, but the end result is easy for us to, you know, judge, you know. But definitely they didn't use SC practices properly. In the system requirement definition, the validation criteria was lacking, probably traceability mapping between the risks and requirements was incomplete because you don't have a correct and complete risk register, and if you don't have that, you cannot do a proper traceability mapping between something that doesn't exist with some requirements. In the design definition, the system design was not created based on the real needs, was not properly evaluated against the real needs, and so on. Their validation process, and I mean, you'll have this slide deck, and please feel free to read. But now, just to check if everybody's awake, let's look at a question that, if anything is going to be asked of these material, it most likely is in this form. They talk about the scenario and then a question. So here it goes. A software-controlled medical device, the Therac 25, was responsible for multiple fatal overdoses due to race conditions and lack of hardware interlocks. Okay, this is just a brief nugget of what we talked in that case study. The question is, which SC process was most critically underutilized in the development of the system? Technical planning, verification, acquisition, transition. Feel free to, I see some B. Great. Yeah, verification. That's correct. They failed to verify and validate software safety features, which cause critical harm. So good job. Now we're going to the next case study. Unlike the previous one, this is a successful case study. Horizon Bridge connects two countries together. And this is kind of what Wikipedia page shows of this. Looks beautiful. This is the world's largest composite structure, and it's implemented in an area that counts as Europe's eighth largest economic center. It is 10-minute drive or train ride, about 5 miles long, and the cost was $3 billion. It is the longest cable-stayed bridge span in the world, carrying motorway and railroad traffic. And its main span is, half a kilometer, roughly. And it has two decks. Upper deck is a 4-lane motorway. Lower deck is a 2-track railway. So it has both modes of transport. So SC Handbook says development stage began with a well-defined time, budget, and quality constraints, right? They knew what they're trying to accomplish. They had it took 7 years for them to develop that, in the design space, 4,000 drawings. And also, interestingly, the stakeholder coordination was good because there were no disputes or major claims, which kind of caused by a strong partnership spirit. The handbook says success of the development stage is clearly based on the concept stage, because the project was binational, meaning that the context of it was beyond one country's rules, regulations. It was needed that at the top, the royal families, they had, good agreement to move forward. And, when you have support and sponsorship from, top level decision makers, it can be successful at the end. Some of the specs: design life 100 years, 4 years in construction, Uh, they considered what should the structure be able to withstand if there's a ship impact. So they did a thorough, analysis of their requirements. They did a proper risk management and safety analysis. And because of their safety analysis, they did some changes to the design. They increased the navigation span. Uh, they modified the channel to they reduced the chance of ship groundings. Uh, Also for environmental protection, they created some islands, artificial islands. That was interesting. And the handbook says they use functional safety analysis and fault tree and what if techniques. Uh, and also a big project, large infrastructure project like this definitely has a large or significant environmental addendum. So they did that. At the end they did not reduce the salt and oxygen flow into the Baltic Sea. They didn't want to change the ecology of the environment. No net environmental impact. Uh, Seabed dredging spillage was limited to 5% of the total dredged volume. And they use modeling. The design was validated using two independent hydrographical models. So they use lots of modeling, including this. Uh, they created two islands and one peninsula, and uh, it was there has been a lot of interest in publishing and studying the factors that caused this project to be successful. And the handbook says this is a clear example of benefit of a solid concept stage, and where the project management team resisted customer-driven temptations to rush development and instead thoroughly planned for long-term success. So that's one of the main takeaways from this. Now for the question, again, the same format. Scenario: the bridge project required coordination between Sweden and Denmark, involving structural, legal, and railway systems. Question is, which process area is most relevant to resolving regulatory and stakeholder conflicts between countries during system development? A, implementation, B, stakeholder needs and requirements, C, agreement processes, and D, configuration management. Please feel free to put the answer in the chat. I see a C. Thank you. I see. Oh, that's for previous one. Anybody else? B, thank you. C, thank you. Uh, so the correct answer is agreement. Remember that because this was a binational infrastructure project, uh, agreement at the top is really the key because you're crossing the borders of two countries, and with the scale of this, that helped the agreement, at all levels. For B, I can see why you chose this. I mean, stakeholder needs and requirements, they're definitely define understanding needs, the real needs, and putting them into the form of requirements was definitely a good and important factor. But looking at, we are trying to find the most relevant one, and uh, regarding conflicts and regulations, this kind of leads to agreement processes. For the third case study, this is about cybersecurity case study for a A software bug or a virus attack on a cyber physical system. Uh, One of the attack vectors was the Siemens PLC uh, that they were using inside that plant, and we're going to talk about how things unfolded. So everybody is now aware that cyber security is a big factor that we should be considering as SE practitioners. And, you know, there are actually security requirements. There's a publication in the INCOSE library about defining security requirements. If your job is about that, it could be a good resource. So this case happened in 2010, and it was one of I mean, at the time it was something that nobody has seen before, something like that, and uh, the degree of attack sophistication was previously unseen. Uh, so the takeaway is that as the cyber physical system attacks are becoming increasingly prevalent, SE should consider implications of cyber to reduce those vulnerabilities. So uh, definitely there are going to be more security requirements, more involvement between software and system. Uh, that's I mean that's already the trend. Uh, so the physical aspect of the security was okay. They had reinforced concrete under a thick layer of earth, all of that. The issue was the network or cyber security. Uh, the industrial control systems or PLCs, programmable logic controllers, these were, even though they were disconnected from the outside internet, somehow they could infiltrate using insider collusion or non-malicious insider insertion of USB drives from outside. And actually, they think that it happened because of service technicians visiting to serve service and supply chain intervention. So even though there was an air gap, meaning that the network was isolated from the internet, but they did not consider the human factor, the fact that somebody could be colluding inside, or maybe somebody makes a mistake by inserting a USB where they should not insert it to. So that's a takeaway. The Institute for Science and International Security analyzed this, and they say for a virus to be able to effective, they need to know what to do. They need to gather intelligence. And after they looked into the software and they looked at the source code, they saw that uh, they had targeted that specific location. So the functionality of Stuxnet it was like a volcano. It was dormant if it was not there in other sites. But when it got to here, they knew that virus knew it was at the right location and started its you know malfunctions. So the important thing for us is to consider that adversaries will attempt to gain intelligence on a system, and we must consider methods to prevent this. So this is really a teamwork with the cyber security experts and people who are looking at the system in its totality, right? The SC practitioner. Uh, it's mentioned that in the handbook that we need to be prepared for many different attack vectors, including internal threats. And we should consider them during system design. You know, there should be it should be well thought of before the zero-day attack. And this case study showed that uh, these kind of viruses could jump the air gap. Even though they disconnected from the internet, they did not consider that, or didn't consider it enough that they could, the adversary can transmit the virus through a USB removable media device. The supply chain for PLCs and the PLC maintenance personnel, there were two additional attack vectors. And we also need to remember, always remember that threats to the system are both inside and outside the system. So human factor, or either being intentional or non-intentional, all of that. We need to prepare for situations like this after a successful attack has occurred. Oh, this is after the fact. It's saying that the Stuxnet was not a static, thing. A program. It was able to update itself dynamically. Could be updated and changed over time. So in the case that the attack occurred, so we failed at prevention, it's saying that we should be able to perform in the mitigation or withstanding the threat, right? So the best thing is to prevent, but if something happened, be prepared that it might be a dynamic software or program that needs, serious mitigation. Uh, yeah, as things are getting more digital, connected, we should also shift our mindsets to adjust. Systems are becoming more and more software centered. So the system design phase is the most cost-effective place to kind of plant your mitigation strategies rather than firefighting. So system design stage is the best, and then the right place to think through as much as is possible. The lesson is we need to understand the threats for the systems, be cognizant that attacks can and will occur, and be proactive in protecting the systems. So the cybersecurity also needs full engagement of SC. So they cannot just do their own software work. They need to consider SE, supply chain. They should consider all of that. So the question here is, for the scenario, an advanced virus targeted PLCs controlling uranium centrifuges, manipulating their behavior while masking it from operators. The question is, what SC specialty area could have most effectively prevented the attack's success? A, maintainability engineering, B, interface management, C, cybersecurity engineering, D, verification planning. I'm looking at we have a C here. And B here. And let's give it another 5 seconds. And the answer is C. I can see why you picked the interface management, because yeah, I mean the virus was able to pass through the interfaces, air gap. So this is kind of the trick option. But interface management is about all the interconnections of the systems. It's not just about the cybersecurity things or problems. But when we talk about the specialty area, it should be really directed towards the problem, cybersecurity engineering, but yeah, there should be involvement from interface management as well. So that to some extent makes sense. Case 4 is about design for maintainability, incubators. And I'd recommend looking at this webpage, Design That Matters. It was interesting for me to look at it. So here we go. In the late 80s, 70s, in Paris, someone called Stéphane Tarnier. So this is about like how ideas come into our heads, right? He went to a zoo and saw, they had farm animals. He saw a chicken incubator, and that, sparked the idea that we can put human newborns in the incubators to help them, you know, they're really vulnerable when they're born, and these incubators help them to survive. Their rate of survivals increased significantly by this idea. Before that, 1 in 5 babies died before learning to crawl. So especially for low birth weight newborns. So Tarnier installed his incubator for newborns at a hospital in Paris and did a study on 500 babies, and it was groundbreaking. Before that, 66% of low weight babies died within weeks of birth. But after this intervention or this solution, only 38% died because of the incubating box. So it was a proof that validation of the solution, and many of the hospitals, utilize this idea. Even now in our modern time, in the hospitals, we have modern incubators. They do high oxygen therapy and other advances, and it's a standard, uh, which has helped to reduce 75% in infant mortality between 1950 and 1998. So that's for US or American hospitals, but in the developing world, the context is different, the story is different. So even though the infant deaths are below 10 per thousand, but in the Europe and US, uh, over 100 infants die per thousand births in countries like Liberia and Ethiopia. Many of them premature babies that would have survived with access to incubators. So they don't have access to incubators. That's the reason, because of the cost, and not only the cost of acquisition or purchase, but also if something breaks, replacing it would be very expensive, needs skilled workers to be able to do that. And the whole chain is broken, in countries like Liberia and Ethiopia. Following the 24th Indian Ocean tsunami, a city of Malabo received 8 incubators from multiple organizations. And somebody from MIT looked into what was the fate of those 8 incubators after 4 years. And he saw that all 8 were out of order. They had issues such as power surges, tropical humidity, and the hospital's staff's inability to read the English repair manual. So this is a trend. Uh, as much as 95% of medical tech donated to developing countries breaks within the first 5 years of use. So maintainability becomes as important as acquisition of those technologies. Uh, so he found an organization called Design That Matters. And what they did was they tried to solve this by using automotive parts to make incubators. That was their solution uh, to to design something that would break in a non-catastrophic way. So if something happens, they can find an auto mechanic that could fix it instead of waiting for someone coming from overseas or for repair. So they built an incubator out of parts that were already abundant in the developing world, an automotive, and I think it was Toyota or something. Uh, yeah, the seal beam headlights supplied the crucial warmth. Dashboard fans provided filter air circulation. Door chimes sounded alarms. You could power the device via an adapted cigarette lighter or a standard issue motorcycle battery. So uh, they reduced. I mean, they made it much easier to maintain and do replacement of broken. I mean, to fix issues. And the handbook says sometimes the highest tech solution is not the best. Simplicity sometimes, is much preferred. And when proposing a solution to a problem, we should consider the whole life cycle, not maintenance, logistics, all of that, besides the concept and development. So the question is scenario. Hospital incubators showed in-service failures due to poor access for repair and limited diagnostics. Question is, which of the following best reflects a SC response to the maintainability issue in the scenario? A, increasing manufacturing tolerances. B, modifying the mission definition. C, applying a maintainability checklist in the design phase. And D, reducing component redundancy. So please put your answers in the chat. We have a B, C, CBC. Thank you. And uh, it it makes more sense because of right here, maintainability. So think about that upfront in the design, and so that's kind of very important. I mean, the main point of this, I can see why you picked B, modifying the mission definition. So I think uh, the mission is, I mean, measures of effectiveness in both cases would be the same for both incubators, but the mission is kind of not inclusive of the maintenance concept. So if it was saying modifying life cycle concepts would have been would have been a valid response or choice. But mission in both cases is the same: save newborn babies, and modifying that would not be very effective. And the last case study is about how AI and SE, work together, impacts of both together. And we can see this car that crashed into this poor person, Elaine Herzberg. And this is an automated, you can see the Uber, and this is a Volvo. Um, it had LiDARs, radars, camera, and object detection was part of this game. So let's see what happened. On March 18, 2018, a pedestrian walking a bicycle was fatally struck by a Volvo car, Uber vehicle, under automated driving. And so this system was developed by Uber's Advanced Technologies Group. So they kind of overrided the vehicle's own advanced driver assistance systems and they disabled it. So we can just see that they kind of canceled a redundancy mechanism up front. And maybe they had the reason was to prevent conflicts with its radar, which operated on the same frequency of the radar for Ubers. But they could have used this technology as well to add another, redundant layer. But that was the problem. The issue that happened was they attributed to classification of objects on the road was not done properly. So that person was on the highway with a bicycle where they should not be. And their software or AI was not trained to detect such, entity. And they, the AI was confused. What is this? What am I looking at? Is it the vehicle? Is it the bicycle? Unknown. And at the same time, the driver was not engaged in this, process, and the handbook says he was checking his phone or something like that. So eventually, that was catastrophic. And this is about designing interactions of a human and the machine from a team's perspective. Uh, so it recommends that changing the unit of analysis from individual humans or individual programmable machines to teams of human and computer. So the issue again was classifications of the object was back and forth into multiple things, and the AI could not decide what is the entity that it's looking into. It didn't have a predicted track, and another flaw. And also one other issue that in the design had was they gave a 1 second hysteresis that if uh, it didn't do anything for 1 second if to avoid false alarms in the case that it was confused. So didn't use that 1 second, uh, gap or opportunity window to save that person's life. So here's the sequence of events. This is the impact. 5.6 seconds before that, that was the first time the radar detected something, right? Didn't know what it is, it just detected. Minus 5.2, the LiDAR detected it first, right? And then the first classification or labeling was this is a vehicle static, not moving, non-moving vehicle. So, but then 0.5 seconds later, it changed the classification to other static. It's not a vehicle. It doesn't look like a vehicle to me. After 1 second, says, oh, this is a vehicle. This is not other, this is a vehicle. After 0.1 seconds says, oh, this is a bicycle, not a vehicle, but it's static. About a second later, as it's getting closer, this is not a bicycle. I don't know, unknown. And then 1.2 seconds before the crash, it says this is a bicycle and hazard. And then because it was confused, it waited for 1 second to alarm to activate the audible alert. And that was too late. And I mean, after that, the operator control was kind of 0.02 seconds before the impact, too late, and there's delay in human response, zero 0.7. The brakes were applied after the fact. So this shows the sequence of what happened. The conclusions and lessons learned was that the operator was distracted by their personal cell phone. The pedestrian's blood indicated impairment from drugs and that they violated Arizona state's policy by jaywalking. So kind of everybody, they did something that they were not supposed to do. And the ADS or automated driving system was indecisive, partly because the pedestrian was somewhere that was not supposed to be, but now they design these systems considering that maybe someone is walking in the highway, right? So Uber had inadequate safety risk assessments, ineffective real-time oversight of the vehicle operator to see if they're, attending to this situation, and the safety culture, and the Uber ADS was functionally limited. Uh, we saw that it couldn't classify the object as a pedestrian or bicycle vehicle unknown, and couldn't predict their path, and couldn't assess risk until almost impact. So the handbook says they kind of fixed it after that. The decision to suppress action for 1 second to avoid false alarms increased the risk, lost that opportunity window, prevented braking from being applied immediately. And again, going back to the first point, by disconnecting the Volvo's own safety system, Uber increased risk by eliminating the redundant safety systems for its ADS. So since corrected, meaning that now they're more redundant. So that's good. The conclusion is that AI, or machine intelligence, we should consider that operating as members of a team. And if the AI perceives a change in the context and environment, they should communicate with the human or human partners. That affects the whole team's performance. So it's kind of suggesting that both parties should relay their understanding, even though imperfect, so they can complement each other. And it's saying Ubercar was a poor team player, and uh, interdependent interactions among the teammates are important. Perfectly. And for SC practitioners, we must be cognizant of the benefits and downfalls of AI autonomy. It's making things more complicated, and there should be some preparation for that. And the question is, an engineering team is developing an AI-driven autonomous vehicle. Challenges arise in tracing decision-making logic during system validation. Which SE process is most critical to ensuring the AI system's behavior is traceable to requirements? A, stakeholder needs and requirements definition. B, verification. C, design definition. And D, requirements traceability. Two Ds. And there we go. Yes, it's about requirements traceability, uh, functional allocation, who does what. AI decisions must be linked to specific system level and stakeholder requirements. So that's kind of the point. And Greg says, but they're all important. I agree with you. Absolutely. Yeah. These are all part of it. It's kind of a test taking, um, it's a trick question. What is the most important one? So that's the way I would look at it. And one thing that I recommend is looking at CBOC. They have lots of interesting case studies from medical radiation. This is actually the THERAC. And design for maintainability is for the incubators, but none of the other three, I think, is here. But so there are only two of the SC handbooks case studies in the CBOC with more elaboration, but there are more, GPS, Hubble Space Telescope, NASA's mission to Saturn, air traffic control, complex adaptive operating system, telescope, all of these things. And the nice thing is you can find which one case study to look at based on your need. Like if you want to look at the stakeholder needs definition, there are many case studies, but if you want to just look at service systems engineering, you have 4, and you can pick and choose which one is more relevant to your interest. And yeah, thank you so much. Any questions or comments or feedback?
Hey, really appreciate that, Sadra. And just like
Sure,
yesterday, really appreciate your time here. Eh,
absolutely.
excuse me. And for those on the call, definitely fair game for not necessarily the exact details of all the case studies. So again, I don't know exactly the case. However, you may potentially be poised a particular situation or scenario. So all these are very, very uh, good, at least to review in the SE Handbook. And by the way, in the book, as you've probably seen, it's a relatively short section, so really quick read compared to the other sessions and the other sections of the book. But I also, for your own edification reference, excuse me, I would, if this wasn't already mentioned before, but go to the SE Bach online. It is a free, open source, huge repository of data for systems engineering, and it gives you a button right up front where you can click it and download the entire thing. It's probably about 1,300 or so pages. It's big. So because it is open source, it is more than I'm sure it encouraged, but it's kosher, if you will, to throw that in any kind of like chat IPT, GPT of your choice, whether it be Grok or 4.5 GPT, and use it to kind of sort through all that information, search for case studies, kind of maybe even generate some test questions. Again, that's just like at your own risk. However, if you'd like to parse through that huge amount of useful data, it is free and open source. Let me see if I can look that up real quick and just post it in chat. While I'm doing that, also, I did upload Sadra's presentation from today and yesterday, same presentation, to the session 12 folder on the both the Thursday and the Friday cohort Google Drives. So you should see the, so thanks again for that, Sadra, for providing me the updated brief slides. And it
Absolutely.
is there. And let me copy and paste the link to the chat. So again, highly recommend that you take a look at this, and you'll see when you go to the wiki, excuse me, sorry about that. There is the download the SE Bach blue button on the right, and you should see it right up front. And I believe when I did it, it downloaded it as a PDF. So a lot of information in there as you start scrolling down, and really good just for your back pocket. So that being said, anything to add, Greg?
No, I think the case studies are very interesting. I love how you can actually see the implementation of everything we've learned.
Good stuff. Yeah, I'm definitely curious to go through see all these other case studies that's in the CBOC as well myself. So with that, please reach out for us or for any questions to us. And as long as you, excuse me, take the exam by the end of the year, you'll get your $50, or at least show whether you pass or fail, regardless. Hopefully, you'll pass, and just show us the receipt of you signing up for it, and that'll complete that reimbursement to you. I really wish everyone the best of luck taking the exam. And again, reach out to us if you have any questions. That being said, I'll stop the recording and I'll be here to support. Thanks, everyone.
Thank you, and good luck with your exam. I hope you all ace it and become certified. And thank you,
Absolutely.
John. Appreciate
Of
it.
course. Yeah. Thank you. Appreciate it. Thanks so much.
Absolutely. Have a great day.